So today we will be talking about security feature. Right? This course name is Industrial Control System Design with Security. Right? So security stuff. So that is the last topic. This one, email, please. Okay, so as we all know, right, security is so important aspect we have to consider when you design a computer system, right? So CPU vendors are making their efforts try to provide the TEE environment. This TEE, trusted execution environment, hardware environment. So for example, Intel, right? x86. Intel is providing some architecture called software guarded extension, SGX. Okay. That is Intel's response to TEE requirement. And AMD is also providing secure architecture called SME, secure memory encryption, and SEV, secure encrypted virtualization. And RISC-V, it is open architecture. They are releasing instruction set, and some institution and companies are proposing the TEE architecture for RISC-V. Right? So examples are multi-zone, and I think keystone. Those are examples of the TEE architecture for RISC-V. And ARM's response to TEE requirement is called TrustZone. So it is hardware architecture. Right? So from software people, we need to utilize the hardware feature to implement more secure system. Right? So hardware the architecture. The thing is, every CPU vendor is making some efforts, right, to provide the TEE environment. So let's talk about now TrustZone. What is TrustZone? This one. Okay, so TrustZone is offering two different worlds. So without TrustZone, there is only one world, one environment. Right? But with the TrustZone, you have two different environments. The first environment is called the normal world or non-secure world. Normal world, normal, non-secure, non-secure, which is normal world, and secure world. Secure. So two environment, normal world and secure world. So sometimes you need to make switches between these two. high level view. In normal world, you want to have full software stack from operating system to some applications running on top of that. And when you switch from normal world to secure world, you also need to run. You also want to run some application program, and that application program is executed on top of trusted operating system. So rationale is in normal world, we want to execute untrusted software. For example, Linux, because so many people are involved in designing Linux operating system. So you never know what's happening inside the Linux, right? So you cannot trust the Linux operating system. So you want to run Linux in normal world, and you want to execute only trusted software in secure world. For example, some banking application you design, some stock exchange application you design, and DRM, digital right management software. So only those kind of security demanding applications should be executed in trust secure world. That is the high level view. Okay. Normal world, you want to execute untrusted. Okay. I don't trust Linux because so many people are developing. Right? So you never know what's going on inside Linux. In secure world, you want to execute only trusted, security demanding software. So the thing is, there is also full. This one, normal world, you need to run full software stack from operating system to application software, and secure world, same thing, right? Some trusted operating system, and you need to execute some application, full software stack. And then the word switching. For word switching, ARM is recommending you should go through is gatekeeper. The gatekeeper is called the monitor mode. You should go through this monitor mode for word switching. Normal world to secure world, you have to go through this monitor mode. And from secure world to normal world, you should go through this monitor mode. That is the high level view. So here, so which world you are in, that can be checked by looking at system register called secure. What is that stand for? Secure configuration or control? Secure configuration register. So by looking at SCR, that is a system register. Okay. And the last bit, the least significant bit is NS. Okay. NS. Non-secure bit. Non-secure. If non-secure bit is set to 1, then you are in non-secure state, meaning that you are in normal world. If NS bit is set to 0, then you are in secure world. Secure world and normal world. So it is that simple. So by looking at this, by checking this SCR, you know which world you are in. It is that simple. Let's go back to this one. So from now on, think about this usage case of the TrustZone. This one is one usage case. So we have two different worlds, right? Normal world and secure world. You want to execute untrusted software in normal world, and you want to execute secure software, right? Some security demanding application. probably you design, some company design, in-house design, right? Software in secure world. So the thing is, in normal world, you need to have full software stack from operating system to application program. And secure world, you need to have, these are applications, right? Digital right management, right? Legal access to the digital content, right? Digital right management software and payment application. Some trusted, corporate trusted, right? Sensitive information. Right? So you want to run this application that is executed on top of some execution environment, some operating system, trusted OS. So secure world, you have only also full software stack. So keep that in mind. You have a full software stack. You want to run full software stack in normal world, and secure world, you also run full software stack. And the world switching should be done through this monitoring. So then, so before we talk in detail about this, think about this. That is privilege level and security state. This green is normal world, okay? And this pink is a secure world. And ARM is providing how many different operating modes? How many different operating modes ARM is providing? ARM is providing 9 different operating modes. If you remember, let's go back to check out this. Register here. So, okay, here. So 9 different operating modes, right? User mode, system 1, 2, 3, 4, 5, and 9. Right? 9 different operating modes. You have a monitor mode here. That's gatekeeper. So 9 different operating modes, and this one is very special. Hypervisor mode for virtualization support. So if you go to, so keep that in mind, hypervisor mode and monitor mode. Okay? Except that normal world, you have what? Normal world, you have system mode, supervisor, 1, 2, 3, 4, 5, 6. 6 different operating modes. Right? There's PR1, privilege level 1, supervisor level, and hypervisor mode, and user mode. So if you count 1, 2, 3, 4, 5, 6, 7, 8, so monitor mode is here. So all operating mode, all different operating modes are supported in normal world. That means what? Full software stack and virtualization support in a normal world. So virtualization support and operating system and application support. So that can be done in normal world. But if you switch it to secure mode, secure state, secure world, then you can count, right? Except hypervisor mode. So probably you don't want to run, hypervisor in secure world. That is too much. Right? We want to run only, trusted software. So virtualization support is too much problem. That is why ARM architect decided not to support hypervisor mode in secure world. So you need to have, these operating 1, 2, 3, 4, 5, 6, 7 different operating modes. So why is that? Because you need to run operating system. So if you think about operating system, you need what? You need the timer, right? Timer is you are doing many OS project, right? These days. Then operating system is scheduling tasks in time multiplexed manner, right? So every 1 millisecond, right? 1 millisecond, timer interrupt is generated. Next 1 millisecond, timer interrupt is generated. At this time, scheduler is invoked, right? It is calling ISR, jumping to ISR, interrupt service routine. Service routine is invoking what? Task scheduler. then you can do task scheduling to support that kind of mechanism. Even in secure world, you need to have this kind of operating mode. So interrupt is generated. Think about your secure state, secure world. Right? To run operating system, you need the interrupt, right? So you need IRQ mode and FIQ mode. So while you are running application and operating system in secure world, you may run into some problem, right? Exceptional case. You may run into undefined instruction. You may run into some exceptional abort, data abort, and privilege abort. Software, right? You never know what's going on. Right? What would happen, right? In secure world, you run full software stack. Full software stack. So that is why, even in secure state, you need to have these different operating modes. So in normal world, you should have these different operating modes. Hypervisor support and OS support. Right? So you need this operating mode. That means what? That means so I'm going to go back and forth. Let's read this vector table first. This one. Q1, please.
TrustZone system, you are seeing vector table. Previous rows in the word, and this is the word. Here is vector register. We need a secure vector table to find the reset value. Let's see where the vectors to the secure monitor FIQ, IRQ, data want to exceptions in a vector to the front towards people or secure monitor people. You can compare the
Okay. So in TrustZone system, you have three vector tables. So think about that usage case, and each word you want to run operating system. So that is why like this. In secure world, we were in secure world, right? So far, when we talk about the topics so far, the CPU Cortex A9 was in secure state. So turn on your system, then CPU is in the highest privilege state. It should be, right? Otherwise, you cannot initialize the system, right? You are in turn on the jet mode. Then Jing supposed to be in secure state and with privilege level, highest privilege level. That means you can touch everything, right, in the system. So when you turn on reset, right? You reset, then you are using that interrupt or exception vector table. Secure state. Then do some system initialization. Then probably you can switch it to non-secure state, right, to run some Linux operating system. So in non-secure state, you should have vector table. This vector table. Remember, right? So so now 8 different vectors. You run into undefined instruction supposed to program count is supposed to set to 0.4. You run SVC instruction, software interrupt instruction, supposed to set 0.8 and so on. So vector table, vector table. So the ARM. So what I understand by reading the specification, ARM specification is ARM was trying to make the minimal changes to CPU to support TrustZone. To support TrustZone, ARM was trying to make minimal changes to CPU. Minimal changes, right? So then what extra hardware you need to support TrustZone. Think about that. So you have two words, the normal world and secure world. So full software stack, full software stack. That means you need interrupt vector table here. I, V, T. 8 different vectors, right? Offset 0, and then offset 1, 8. Same thing goes here. Secure world. You need separate interrupt vector table. That's obvious, right? So then, so we know, right? So the start location of vector table should be programmed in vector base register. Same thing goes to here. So this table, separate vector table, you need a system register. Same system register called VAR. Vector base register. But these two are not the same. Physically separate register. We call that banked register. VAR. Banked register. So VAR is banked. Banked means physically separate register. If you switch from normal world to secure world and using MCR instruction, you can touch this VAR. If you change back to normal world, then using MCR instruction, you are touching this VAR register. So banked register. So again, ARM was trying to make minimal changes to CPU. Almost everything inside the CPU is shared between these two. The register file is shared, general purpose register, right? ALU, right? Floating point unit, neon, vector processing engine. Everything, almost everything is shared. But some cannot be shared, right? We are vector base, right? Because you need to use your separate vector table. Separate vector table. So operating system should be executed here. And separate operating system should be executed here. Does it make sense? And what else do you think? What kind of register should be banked in addition to VAR? Think about that, separate operating system, software stack. To run operating system, right? So if you think about Linux, some full blown operating system, the virtual memory is implemented. Then that means we haven't talked about virtual memory and TLB support in this class. But if you recall the undergrad operating system and computer architecture, what you need to support virtual memory? So you need, right? So Linux, right? Linux is running Linux, and some other full-blown operating system is running. To support virtual memory, you need to create page table. Page table is doing what? Page table is doing translation of virtual address to physical address. Virtual address to physical address, right? For every program, every process, every task, operating system is creating separate page table. This page table is for hello world, for example. If you run different program, sorting program, you need to have separate page table. This one is for sorting, your sorting program. So UR program, UR separate page table. So OS create this page table, then you have to let OS Linux know, okay, page table starts from here and here. That means some system register should hold the start location of this page table. In ARM, we have translation table base register. TTBR, translation table. Translation table. This is translation table. Virtual address to physical address. Translation table. So TTBR, that is system register. We have VAR register system, and TTBR should be programmed to indicate the start location of this page table. So that means every time you do context switch, right? You are doing context switching. You are writing context switching code, right? For mini project, right? So every time you do context switch, TTBR should be programmed, reprogrammed. Okay, now it is time to execute sorting program that should be pointing this page table. So your program is program to indicate this. Right? So in secure world, right, you want to execute, right, many different, several different, the programs, right, on OS, right. So you need, separate the page table. This one is for DRM, digital right management application, for legal access to digital content. Right? So, and this one is for banking application. Right? You need separate page table. How exchange, how exchange Bitcoin program. Right? So you need to have separate page table for each application program. Then you need to say, okay, now my Bitcoin program start from that phrase. Right? You need separate TTDR register. So you do all the switching, right? You need to have separate copy. That TTDR is not the same as the TTDR. These are banked, right? Banked register. It's a physically separate copy. Physically separate. So that is why I keep saying, right? ARM is trying to make minimal changes to CPU, minimal hardware changes to CPU. Almost everything is shared except those banked registers to support TrustZone. Does it make sense? And some only few banked registers are supported. Some banked registers are necessary to support TrustZone. So any questions so far? That is the picture. So you want to run your full-blown operating system. That's what you need to support full-blown operating system. So basically, same the environment, right? Same environment. You need to have IBT page table, response, normal world, secure world, the same thing. Then what you need, right? So if you have that big picture in mind, then things will be very mechanical. Okay? Very mechanical now. Right? Let's move on to this, right? So now let's talk about this gatekeeper monitor mode, right? Monitor mode is again gatekeeper. To switch from normal world to secure world, you have to go through the monitor mode, right? But you can do this if you want, right? But look at this, SCR. SCR register, there is a system register. SCR register, NS bit is indicating which world you are in. NS non-secure bit is 1. Then you are non-secure, right? Normal world. You are in normal world. NS bit is 0, then you are in secure world. But what if you simply change that bit? Yeah, we have MCR instruction. MCR, okay. Co-processor instruction. Using MCR instruction, you can change NSB to 0 or 1. For example, if you are in secure state, if you are in secure world, right? Then NSB is 0. Then what if you change that NSB to 1 by using MCR instruction, just one instruction? You don't want to go through. Monitor mode. We have monitor mode. Then you should go through. Actually, you should go through monitor mode for world switching. But in this case, I don't want to go through world. I don't want to go through monitor mode. Simply change NS bit. What do you think? If you change that to 1, if you go to normal world, come on, I can hear you. No, it is possible, right? It is possible. You have all the privilege to change anything you want, right? In secure world. So if if you want to change NS bit to what using MCR instruction, that can be done. No problem. No problem. You can just force CPU. You can change. That is brutal way, very brutal way, right? You can change from the secure world to normal world. But the thing is that is not recommended way of switching for word switching. Is not recommended to use MCR instruction of to change, simply change that bit. Because think about that. Word switching is what? Word switching. Why do you want to word switching? It is like also one more big picture. One more big picture. So you have full blown operating system running, normal world, and full blown software stack. Full blown software stack, full blown software stack. And why do you want to do word switching back and forth from normal world to secure world? Why do you want to do that? Because of DRM, right? Because you want to run DRM on application, right? Then you need to word switching. So word switching, if you think about word switching, it is like what? Task switching, right? So task switching, right? Task. You want to do task switching essentially. From you are in the middle, right? Normally you are in the middle of executing some application program. Okay. Then you need to run some DRM. Then you need to call, right? You need to call probably system call. So we studied SBC instruction. What is that? Software interrupt instruction, system call instruction. Right? And for word switching, so one way to do word switching is using this special instruction called SMC, secure monitor for SMC. It is like SBC instruction, software interrupt instruction, but you have to use separate instruction SMC, secure monitor for. Okay. Secure this monitor. Secure monitor. You want to go through this monitor. So you have to use SMC instruction. And why do you want to call SMC instruction? Two purposes. First one, task switching. Second, word switching. So stop CPU, only one pitch called CPU, stop executing current application program. Then eventually I want to run this DRM. Big picture, right? In the middle. So this normal world, CPU is in the middle of executing, we have hello world program, right? Hello world program. And then you need to run DRM. So stop executing hello world. Then switch it to eventually switch it to DRM, right? But in the middle, you have to go through this monitor mode, right? But the goal is task switching, right? From your application program, right? Then run this DRM application. Right? So task switching, and at the same time you need to do word switching. There is one difference. For task switching, what do you have to do? For task switching, think about your mini OS project. What are you doing for task switching? One page for CPU, right? So hello world, you stop this program, stop hello world, right? So that SMC. So you want to preserve the state of your application program, because it looks like this. You are executing DRM in secure world, and eventually you need to come back to here. Right? So you need to preserve the state. Preserving state means what? You need to push context, push CPU context to the stack, right? And then pop, right? Then probably before you pop, then resume, right? Resume the process. So it is like the interrupt, right? Interrupt happens, then you need to preserve the state. Then when you come back, you need to resume from the previous step. Right? So mechanism is very similar. So using so it looks complicated, but the eventual goal is I want to start the process program, current program in normal world. Then I want to run this program. Right? So it is in high level it is task switching. And world switching should be done first. So task switching should be done in the monitor. Task switching, these two should be done in monitor mode, this gatekeeper. Gatekeeper, monitor mode, software. You have to implement that software in monitor mode, right? Monitor mode, do what? Monitor mode, okay, you need to push to preserve the state, right? Preserve the current state. Right? Push operation, push context to the state. The state should be prepared separately from normal world state and secure world state, two different states. So push normal world context to the state, then pop the DRM, the state, the context, pop context to CPU register. CPU register should be populated with DRM context. Then we can resume. So that should be done. Push, that is task switching. For world switching inside the monitor mode, you have to do what? You have to check that LSP. Why? Sometimes you want to switch from normal world to secure world. Sometimes opposite, right? Secure world to normal world. So you need to figure out, okay, who called me by monitor mode using SMC instruction. SMC instruction is executed from normal world or secure world. So if that SMC instruction is executed in normal world, in the monitor mode software, read SCR instruction, then SCR register, then NS bit will be 1. By reading SCR register, we know, okay, the call came from normal world. So then push operation should be done to normal world state. And pop operation should be done from secure world state. If SMC call is coming from secure world, then monitor mode software check SCR, system register. If NS bit is 0, right? Because that call came from the secure world. Then push operation. Okay. Push operation should be done to secure world state. And pop operation, because you have to resume. Pop operation should be done from normal world state. So that is big picture. Two things, full-blown, software stack. So the world switching. Why do you want to do world switching? To run, application program, right? So you start current program and execute DRM, banking or stock exchange, whatever. You execute that program, right? And come back. Simply task switching. One difference is word switching should be done. You have to take care of word switching. That is the difference. Okay, let's move on. So monitor mode, right? By looking at this CPSR register, if there is 1 0, 2 zeros and 1, 1 0, 2, 1, 0, then you are in monitor mode, right? Empty. Then one important thing, right? So again, green is a normal world, but pink is including monitor. It is a secure state. So I told you, right? If NS bit is 1, then you are in normal world. NS bit is 0, then you are in secure world. But in monitor mode, it's exception. There's an exception in monitor mode, right? In monitor mode, regardless of NS bit, you are in secure state. Secure state. Secure world. That can be understood. Why? Why is that? Because you are right? From normal world, probably you can call you execute SMC instruction. Then you go to monitor mode. From here you execute SMC instruction. Then you go to monitor mode. SM secure monitor call instruction. You go to that monitor mode. Secure call monitor mode. If you run SMC from normal world, then NS bit is 1. Execute SMC from secure world, then NS bit is 0. But in monitor mode, you are in secure state. Because you have to be in secure state, otherwise you cannot touch. You have some limited access to some hardware. In monitor mode, you can do almost everything you need to do. Because world switching should happen. So the point is, regardless of NS bit can be 0 or 1, depending on where you came from. Right? You came from normal world, NS bit is 1. You are from secure world, NS bit is 0. So that is important. Don't be confused. Right? Monitor mode. So this one. Okay, so let's read some PowerPoint slides, then let me continue. Okay, so this one. You wear a mask. I don't know who is confused. Bonjun? Okay. Okay, this one. Can you please? Mingu, please. Okay, so so far we focused on what? Focused on CPU. So almost everything is shared. Almost everything inside the CPU is shared except some important system registers. How about whole computer system, ARM-based computer system? What is computer system? Computer or embedded system. Computer system. You have CPU, memory, and I/O devices. Okay. That is computer system. We focused on CPU so far. Right? How about this memory and I/O? If you remember the lecture, ARM is doing what? The IP business, intellectual property business, right? So ARM is selling, ARM is licensing its IP core, okay, some file, very low, hardware design to Samsung, Hynix, LG, Intel, Qualcomm. Right? Then once Samsung license their IP, then you can customize it and manufacture actual chip. And the trust zone technique can be applied in hardware design phase. It applies to not only software, but to hardware design phase. So when you license ARM IP core, then design this whole computer system. Let me show you. Let me show you one example. Here to show you one example like this. This one is showing one simple example. Okay, one simple example. So you have ARM CPU, and then 32-bit, right? ARM is generating our Cortex A9. Cortex A9. Let's assume Cortex A9 is providing 32-bit physical address. Physical address. That means it is creating a 4 GB memory space. 4 GB memory space. Now you are in hardware design phase. Okay? So you need to populate space, right? Space means actually nothing. At the beginning, nothing. You need to populate actual hardware component, memory and I/O devices, and create memory bank. So in that example, I want to place 4 GB. Let's divide that into 4 pieces. First, 1 GB, second 1 GB, and the last 1 GB, 4 GB, right? So I want to place actual memory here. Okay? 1 GB memory, start from 0. Okay? And second 1 GB, I want to place another memory. And that memory should be accessed, green, right? Green means secure word. When I design this computer system, okay, 1 GB memory, I want to make it only accessible when you are in secure state. In other words, SCR, NS bit is 0, NS bit 0, then CPU can access that memory. Okay, and this one is normal world memory. This one is secure world memory and normal world memory. So normal world memory can be accessed regardless of this NS bit, meaning normal world, right? Normal world memory. That means CPU is normal world, then you can access this memory. What if you are in secure world? CPU is in secure world, yes, it's 0. Then still, you are still able to access normal world memory. You have enough power, right? Secure world, right? Everything you can do. Right? So, but normal world can be accessed in a secure state and normal world both. Right? But secure memory can be accessed only when you are in secure world. Secure world. How would you design that kind of configuration? Simple. Right? So using that decoder, so 1 gigabyte. Right? So decoder, right? Only one output is hot, one output is 1. Depending on these three inputs, then 8 outputs. Right? Decoder. 0, everything is 0. If you remember decoder, let me use this 2 to 4. 2 input, A0, A1, and 4 outputs. Y02, Y3. A0, A1, 0, 0, then Y0 is only, Y0 is 1. Okay. 0, let me change. 0, 1, then Y1 is only 1. So 1, 0, Y2 is 1. 1, 1, Y3 is 1. A decoder. So by using the decoder, we can create memory map. So for 1 gig each, 1 gig each. Then by looking at the most significant 2-bit, right? 32-bit address, right? By looking at the last 2-bit, right, 0, 0, then you are talking about that, last, 1 gigabyte, right? 0, 1 is 2-bit address, right? Address 31, address 30, address 0. So 2-bit, right? You can say, you can tell one of these, 4, right? 1, 0, and 1, 1. 0, 1, you are talking about that memory. Okay. So address, right? So if I write address, then 0, 1, right? Everything is 0, then first location, right? So 4, 0. So what is the location of the third? Start location of this memory. It starts with 1, 0. Everything is 0. The remaining 30 bit is 0. Then start location. So 8, right? 0x 8. How about less one? 1, 1, 30 zeros. Right? So that means C. So by looking at this 2-bit, you can tell which memory you are talking about. Okay, that is one thing. And then one more important thing you have to check is to create the hardware system. So that is address, and then actually your data bus, data line should be connected to memory, right? Address and data. That is obvious, right? In addition to data, address and data, control information, control signal, hardware signal should be delivered to memory and IO device. Why? Why is that control signal? What do you mean by that? Sometimes, right? Sometimes you are executing LDR, sometimes SDR, read and write. Memory read or memory write. IO device read and write. From CPU point of view, right? Only read and write a transaction. Right? So for read and write, you need to deliver that information, right? What kind of transaction do you want from memory? I want to do read operation, LDR. I want to read some data. So by using this control signal, that information can be encoded. For example, 0. Let's say 0, you execute LDR instruction, then CPU is generating 0. 0 means read operation. Read operation. Okay. So if you execute STR instruction, memory write instruction, that control signal will be 1. CPU will assert that line, so that write operation. So when you design, the system 0, then memory is responding and providing data. One, then data. This data should be written to memory. So at least the point is to make connection from CPU to memory, CPU to I/O devices, you need at least these connections. That connection is defined by what? AMBA protocol in ARM case. AMBA protocol. So XE actually. So there are several versions, and these days we use XE. XE, Advanced Extensible Interconnect. There is ARM, bus protocol, extensible interconnect. Okay, right. So XE interconnect is defining the detailed mechanism to read from memory and write to memory transaction. Right? So one of very important control signal you have to look at is that control signal, AXPROT. In addition to this read and write, the ARM is also generating a X means read or write protection, PROT. This first bit, I think. So that bit is I have to, the 0 means what? 0, 0, 0, 0. Then you are accessing. Secure memory, secure the last one. Then should be 0, 0, 0. Okay. So AXPROT is 0. AX read or write 0. Then you are in secure state. You are in secure state. CPU, secure state. You execute memory read or memory device, right? IO read or memory read. Then that line, that wire will be 0. Okay, you can take it 0 and 0, right? That means you are executing this program in secure state. Secure state. If you execute same instruction in normal world, that line will be 1. Hardware, right? Hardware is designed that way. That is a protocol. AX protection is 0. Then CPU is executing LDR or STR, read and write transaction in secure world. CPU in secure world and executed LDR, STR. Then that is indicated by that signal. Take 0. Normal world, right? CPU is in normal world, execute these two. Then that AXPROT will be 1. That is the protocol. So by using this line, you can design this whole embedded or computer system. You can say, okay, that memory should be accessed. That memory should be accessed only when CPU is in secure state, secure world. That memory, second memory, should be accessed either in normal memory, right? Normal world and secure state, you are still able to access that memory. So how to make the corrections? So that is how the block diagram. So take a look at that hardware, schematic. So in for normal world, right? Let's talk about normal world. You are in normal world. Normal world, right? Then AXPROT supposed to be 1. Then you are targeting what? A secure memory first. Sorry, secure state. AXPROT 0. Then the first 1 gigabyte is allocated for secure world. So that means A address 31 to 2 bit, last 2 bit in address should be 0, 0. Because you are reading from that memory location, right? So everything is 0. AXPROT 0, 0, address 0, 0. All 3 bits are 0. Then Y0 is asserted only. Y0 is 1. Okay. That is connected to chip select. Okay, so first, right, explain chip select. So every hardware component, memory and I/O device has one special connection called chip select, one input connection to chip select. As the name implies, chip select, right? If that is one, then then that is indicating that guy is selected. Okay. So to access, in other words, to access the memory, you have to make sure you are providing one to the chip select. Chip select, right? That input. I mean that guy, you are selected for access. Okay. So then look at this. All 3 inputs are 0, then Y0 is 1, then chip select is 1, then that guy is selected for access. So how about that case, normal world, right? Normal world, the second 1 gigabyte, right? So address 31 to 2 bit is 0 and 1. And AXPROT will be sometimes normal world 1, but that memory can be still accessed when you are in secure state. Okay? So in secure state, you can do this, right? Secure state, AXPROT. Secure state. So first one, secure state 2. You are still access. You can still access 0, 1. Then AXPROT 0. Right? No more word memory, right? Then memory still can be accessed when you are in secure state. When you are in secure state. So let's talk about this, right? So then the first connection 101 decoder input 101. So that is 101. There is 5 in decimal 101 5. Right? Now about 001 001 in decimal 1. So that output is asserted sometimes, and Y1 is asserted. So that is connected to OR gate. Either Y5 is asserted or Y1 is asserted. Then you are selecting that memory. Okay. So that means you can access that normal world memory when you are in normal world or secure. That is hardware design, right? So you can make connections like that. So you can, the point is, when you design the hardware system, you can designate or allocate or assign, right? Okay, this memory is for secure world, then memory for normal world. Same thing goes to I/O devices. I/O devices, right? For example, you have a timer, right? You have 2, timer. So first one is timer number 0, timer number 1. Then you want to access that timer only in secure state. Okay. And this one, normal world. You want to access that timer in normal world. So using the PROT, you can do the similar connection. You can make similar connection to achieve that goal. Okay. So the point is, TrustZone technology, right? That starts from hardware design to software programming, hardware to software stack. Okay, so let's go to So and also cache and TLB too. So if you look at this, cache, right? Cache, trust zone enabled cache. So that is each row. Each row is called cache entry. So if you remember computer architecture class, typical cache structure, simple, direct map cache, for example. Direct map cache. You have cache entries. Okay? Cache entries, and you have tag and data. Data is typically 64 bytes or 32 bytes. Okay? So if you miss the cache, then memory, let's use 64 byte. Then 64 byte memory block will be placed somewhere in cache entry, okay, depending on the index, right? And then one more field is valid. This cache entry is valid or not? Then data cache, you have 30 bit. 30. If you update this cache entry, then 30 bit is set to 1. So that entry will be, data will be eventually updated to main memory. So that is typical cache structure. But trust zone enabled cache, you have one more field. That's NS field. One more field. NS, non-secure bit. If that bit is set to 1, that means what? Non-secure, right? Non-secure. Then that cache entry is allocated. That cache entry is normal world cache entry. So cache miss happened, then something loaded here, and that data was accessed when you are in normal world. When you access some data in secure world, secure state, CPU in secure state, you access it, then that probably that is allocated to here. Let's assume. Then NS bit will be that cache entry has been accessed when CPU is in secure state. Okay. So how do you special is NS bit to indicate that access state? Not only cache, but TLB. TLB is the cache. Your page table. We have inside the CPU. We have very special other component called translation cipher. That is taking virtual address from CPU, then provide physical address translation. TLB is doing what? TLB is composed of also entries. TLB is caching what? TLB caching page table entry, because page table contains translation information. So that is caching the TLB. When you cache that page table entry, then it has also NS. Okay, that entry came from page table in secure world. Some entry came from page table in normal world. So NS bit is indicating that. Yes. Oh yes. Little bit. So let's go to there. So one little complication is this. I think someone has been working on this to find out security breach in TrustZone. So look at this one. This means when CPU is in secure state, you are accessing that memory location, 1000 location. And what is this? Same memory location, 1000. but you are accessing that location when you are in normal world. But then these two transactions, two locations, supposed to be two different locations, not same location. That means, someone, what do you think? Can you comment on that? Still, I'm a little bit confused. Still confused. Yes. So let me explain. Right? So with this example, this second 1 gigabyte, let's say, forget about 1 gigabyte. Let's say this is 1,000. What about this second? This memory, normal world memory. So let's say this is 1,000 location. This location, and sometimes that location is accessed when you are in normal world. Okay? And then sometimes you access same location. You can still access your normal memory, right? You are secure state, secure world. Still can access that location. Right? Then that information will be tagged. Right? When you are in secure state, secure and normal world. So secure state generating the transaction, then secure transaction 1,000. And normal world, right? Non-secure transaction targeting 1,000. But you are actually accessing same memory location. But cache will be tagging with that different NS bit. That is correct, right? Right. So assume, then that means what? Normal world. Let's assume normal world you accessed that memory location. Then cache will contain same index, right? Probably index would be different. Index, it doesn't matter actually, right? Right, in my thinking, right? So let's say, so for simplicity, let's assume tag contains 1,000. Actually not 1,000, right? It is supposed to have just a small field, right? 1,000 and some data. Let's say data is just 1. So 1 is stored here. Then normal world access supposed to be NS. NS means 1. NS, right? NS 1. Then you access it from normal world, right? Then next time you world switch it. World got switch it. And in secure world you are accessing same location. Then you search same cache entry for lookup. That, but you generated that secure 1,000, right? So that will be compared. So this tag information is equal, but that information is different. So that should be cache miss, I think. Is it correct? (33번째) Okay, yes. So NS bit, right? But physically, right? Physically you can think everything. You can think everything as address, right? Address, right? So CPU is generating address, 32-bit address. Then AXPROT, right? AXPROT is indicating word, right? So when you look up the cache, then this address information, 32-bit address, 32-bit, is concatenated with that NS bit. Right? That whole information is used to index the cache. Probably this one is index. Then that is tag information. So physically, right, if you think about hardware design, actual hardware design, that this whole tag information, you can think of it as part of tag. Right? NS is also everything is tag. This whole information is compared against this upper part to check it all means. So NS should be the same in addition to the actual this nodulus. I think the someone did many experimentation, figure out that, right? And that is what's happening. 물리적으로 하나가 있는 거지. 하나의 로케이션, 물리적으로 하나인데 이 로케이션을
태그 전체를 아까 말씀하신
NS 비트는 어느 월드에서 액세스를 했는지를 나타내는 거고, 다른 이 두 개의 월드에서 같은 위치, 물리적으로 같은 위치를 액세스했다 하더라도 월드가 다르면 미스로 간주한다는 거지. 월드가 다르면. 태그 인포메이션이 다르기 때문에 태깅을 그걸로 하기 때문에 그래서 미스가 나서 다시 이제 로딩을 하겠죠. Okay, super excellent question. Yes, thanks. Okay, any other question? Time is up. We need to continue next time probably. Okay. So next time I'm going to show you some demo. But we have only one. I have only one lecture, right? So third is one lecture. Then the first day of June, election day. 6th of June, Memorial Day. Then your presentation. So I have only 1 day left. Okay, 1 day for lecture. So probably I have to push a little bit hard next time to show you a demo and some background information too. Okay, that's it. That's it for today.